Thanks for organizing. Contrary to what was advertised, I'm giving a talk called Data Structures for Network Languages. So what brings about this change is that it is Spencer's sort of mission to sort of explain a simple example of the use of category theory and to in particular emphasize what category theory analysis brings to the table. And so I wanted to move to a more simple setting where the idea I want to express comes across better. And this idea is just that this category theory goes a great language for sort of giving very concise definitions. And this translates in practice into sort of simple data structures. So you can specify some minimal amount and then say, do the obvious thing or do the universal thing and generate some larger data structure which would be hard to specify by hand. So a remark though, this is not the talk I'm giving, but I'm around, David's around, and Remy's around. And so if you're expecting me to talk about neural nets, things like that, and draw diagrams like this, then we're discovering cool stuff. The story's still in progress, but we're discovering sort of the structure of backpropagation and how it's linked to things like lenses and databases or composition. But back to the main story. So I want to talk about data structures for network languages. So what do I mean by network? Here are things that you might call a network. And why I like the picture, which I saw from Wikipedia, is that we have two representations of the same network. So at the top is some sort of physical representation where we see both the mechanical system and electrical system and how they're interacting. But you might abstract and look in terms of some sort of flow diagram, and you might abstract again or go to other representations of the system, like system of coupled differential equations, or just some set of states that are coupled, right down to just raw equations. But they all have this network structure, and it's also important that we can translate between these structures. So these two somehow represent the same system. We want to be able to express that sort of thing. So when I say network, you might think of this sort of thing. You might also think, of chemical reaction networks or microprocessors, or on the less diagrammatic side, you might think of certain systems of matrices and sort of more exotic matrix positions in terms of networks, or tensors, that. But when it comes down to it, the raw structure or the abstract structure, they have these things, systems, and they have names like F, and they have boundaries. So F has 3 things coming out. So there's G, or H has 4, and A has 2. And then, given these systems, we can do this thing called networking them, and then we get some big systems. Big system also has a name. And so they divide together in this way, and they have so the big system that's called X. X is the name of the system with three outputs. So this is a very general structure, and it's really only subject to one requirement to make sense. And this idea is that, as we sort of saw in Bob's slides, if I want to, if I want to connect this computer to the wall to charge it, then it doesn't. What's important about this fact is that the operating manual doesn't really have to specify whether I need to get the charger, plug it into the wall, and then plug it into the laptop, or whether I can get the charger, plug it into the laptop, and then plug it into the wall. The sort of wiring diagram is enough to specify completely the behavior of the outcome I want. So similarly, we have ways of combining systems, so F is a system, H is a system, and somehow we have this notion of F wired together with H in this sort of way. So we'll call that A. So if we compose F and A to get F and H to get A, and then compose that with G and K in this way, this should give the same result as doing it this way, right? If I compose F and G together that way to get B, and then with H and K to get that thing, I still get all these diagrams represent the same system. So this is what I'm calling a network language. Also, don't know how to move that, but I'm also going to call this a hypergraph category because that's some jargon that's the literature. So this is a data structure problem, right? To specify a hypergraph category, there's a bunch of things you have to do. You have to list all the names of the systems. You can't really get away from that because everything that you want to talk about needs a name. But then you need to list the composition rule, which says that for all systems arranged in all possible networks, you need to be able to name what the composite system is. And then after you do all that, you need to be able to say that this data, you need to check that this data coheres. So it actually does form a network language. And there are sort of, the reason it's called a hypergraph category is that it's slightly easier than this. The tools of category theory say that we can use, I guess again, Bob talked about, these network things become spiders in most terminology in some sort of symmetric monodal category. But we have to specify, and so what we're doing is just specifying sort of pairwise compositions in various different ways, and that will generate the composition rule. But it's still a lot of data to specify. And this is a good thing because we need the richness, we need this very general data structure to be able to tackle sort of complicated examples of networks that arise through tensors or matrices, when we get down to this method. But you might object, this is a lot of things to specify when things like electrical circuits are really very simple, right? We all kind of know intuitively, if you give me a bunch of circuit components, what the networks I can construct out of those components are. And so the story is something like this. If I have a bunch of components connecting some light bulb up to a battery with two switches where either you and I can turn the light bulb on. To describe what's going on, I'm going to say, well, we're just going to connect some dots. So I'm going to put a witness, this witness says, I want to connect this thing with that thing. I'm going to place it on the page and do that for everything I want to happen. And then sort of clear to everyone from this diagram how this thing turns into that thing. Just combine the things that we said we were going to combine. Okay. So in category theoretic terms, in terms of some universal construction, this is called taking the co-limit or co-equalizer of this diagram here. And what it really comes down to is understanding how these systems just interact with these functions, f and g, that are specifying how to connect things up. So in this setting, to talk about, and this is just jargon, a decorated co-span hypergraph category, we need to specify, again, all systems, but we only need to talk about how systems interact with functions. And then coherence, again, just jargon, and you have to believe me that this is simpler than checking coherence for some sort of hypergraph category. We just need to check that this data forms a lax symmetric monodal functor. So that's precisely the point I want to get across. Universal constructions sort of here take care of the rest. They allow us to specify some sort of minimal data structure for some simple cases, and then take that data we specified and translate it into this big general case so it can play along nicely, be interoperable with more complex cases. But we're free to work in a simple setting as long as the simple setting is enough. And so I guess I should mention that this is being used in practice. So Yellow is implementing these ideas in his work with Slatebox, and I think John and John are doing this in their work with Petron. So I put these up, there are some papers on my website. But the last thing I want to mention, the main point is, again, universal constructions are great. But the other thing I want to mention is that David and I put this book in the archive yesterday. So one of the things I noticed in the surveys that Spencer sent out was that a lot of the industry people said that exposition was one of the main things that they wanted out of the academic side and category theory. So we've written this fairly short, it's 250 pages, 7 chapters, it assumes no category theory. But the aim is in each chapter we pair some representative sort of real-world type example with some concept and category theory that we think, that the concept kind of represents the key intuitions of. So, yeah, I'll leave that slide to look at. Highlighted chapter 6, just